So let us see the relationship between A and G, Young's modulus and restrictive modulus. Okay, so we know these definitions, right? Young's modulus is equals to tensile stressor, compressive stress divided by strain, and whereas G is equals to shear stress by shear strain, ratio of shear stress by shear strain. Okay, so in order to establish a relationship between A and G, okay, I'm going to consider a body, okay, a body of square cross section. So if A is the length of this side, each and every side will have the length A, right? So A, B, C, D is the solid body under consideration. Now this TB is a diagonal. Okay, and AC is also going to have a diagonal. Okay, you know diagonal. Diagonal is a line that is connecting two opposite corners of a square or a rectangle. So now, what is the length of the diagonal if the side of the square is A? So if this is A, the diagonal has a length of A root 2. You can say that the length of the diagonal is A in the sense this or this here, right? You can write this as A. Okay, so AB root 2. Okay, so let tau be the shear stress acting on this side BC. Okay, so now when the shear stress of tau is acting on a square body whose length or dimensions are A with a diagonal DB and AC, what happens is the deformation is going to develop inside the body, right? So now the body is going to deform. Okay, if you see this figure over here, so this figure actually represents the deformed body. As you can see here, this A, B, C, D is the original shape of that body, right? Original shape. But what is happening is because of the shear stress tau acting on the side BC, this is going to deform. Okay, so since there is a friction between the surface which is holding it here, okay, holding it here, and this side AT, this does not move directly just like an object. See, if, for example, this is an object, if I just push, it is moving forward, right? Isn't it? If I apply tensile force, shear force, it is moving because the friction between this body and the ground surface which is holding is very minimal. But let us take that AD is supposedly fixed, okay, at the bottom. So what happens is now if you try to push it by applying a tensile stress over the top BC, the body is going to deform. So the red dotted colors denotes the deformed shape of that body. So now the deformed body is A, E, G, D. So as you can see, A, B, C is the original shape and AEGD is the deformed shape. Okay, now let me remind you that the angle which is between each side is 90 degrees. So this is going to be 90 degrees, isn't it? So now this angle is going to be 90, this angle is going to be 90, this angle. But what happens to the angle between the sides after deformation, after deforming of this body? Okay, so here, as you know, when the shear force is applied, this phi is nothing but the deformation, angular deformation. Okay, so in case of tensile stress and compressive stress, you have deformation in the terms of meters, centimeters, but here you have in terms of angle. There it is linear, here it is in angular. Okay, so now EG is the side after deformation and EA is the side AD is the side and DG is the side. Now, the angle between two sides, EG and EA, will that be 90 degrees? Will this be 90 degrees? This angle? No, it won't be. Okay, right, because it is deformed. The sides are deformed, just like this, for example. Let me take this. So, this is the shape. This is the shape. Okay. Now, so if you can see this angle over here, this cannot be 90, isn't it? This is 90 degrees. This is not 90, isn't it? But as you can see, this phi which is developed, the angular deformation is very much minute. Of course, I showed you, I enlarged this figure. Okay, I draw it with a larger deformation here. Okay, but the body will not go this much of deformation. Okay, that is, as phi is going to be very small, this angle is also going to be nearly equal to 90. May not be 90 exactly, but it is going to be nearly 90 degrees, something like 88, 89. So we approximate that angle to 90. Okay, so now initially DB is the diagonal, but now after deformation DE is the diagonal. Therefore, as you can see in this figure, a diagonal, okay, divides exactly the angle between sides, right? So if this is 90, angle between this diagonal and this side is 45. So therefore, DE is the diagonal. Therefore, the angle between this and this is 45 degrees. Okay, so this is the figure here. Now, now the interest here to me is the calculation of strain in the diagonal. Okay, so let's see in this figure. DB is the initial length of the diagonal, but as you can see here, DE is the length of the diagonal after deformation. You can clearly see the increase in length or increase in dimension of this diagonal, right? So let us calculate the deformation strain in the diagonal DB. DB లో వచ్చిన strain calculate చేద్దాం. So in order to calculate strain, we have very simple expression. What is that? Change in length of the diagonal divided by its original length of the diagonal. Therefore, so see here, DB is the original diameter, whereas DE is the diagonal after deformation. Okay. The difference between length DB and DE is the change in length of diagonal. Okay, divided by original length of diagonal is DB. Okay, let me show you by deriving it. So as you see, let us consider a diagonal BD. Okay, strain in BD diagonal, okay, which is a diagonal, is equals to change in length of the diagonal divided by original length of the diagonal. So change in length of the diagonal. What is the change in length? So as you can see here, okay, I can project this B onto this diagonal. Okay, if I draw a perpendicular line to this perpendicular line, this DB length is going to be equal to DF approximately. Okay, almost. Okay, this DB is equals to DF. Okay, how can I obtain this point F is just to draw a line perpendicular to this line from B. Okay, so now DB is equals to DF. Okay, so now if DF is equals to DB, DF is the original length of the diameter. So we can say that, right, isn't it? You can write instead of DB, DF as original length also. Now, what is the final length of the diagonal? DE. So DF is the original, DE is the after deformation. So the difference between them is EF. So EF is nothing but change in length of the diagonal. Therefore, see here, dE, in this equation, dE minus of dF from here to here divided by dF, original length. Okay, original. So final length minus original length will give you change in length divided by original length. So since phi is small, dF is going to be equal to dB. As I said earlier, this is going to be approximately here. So I'm just replacing it with dB. So d minus of dB divided by dB. Okay. So therefore, strain in diagonal dB is equals to, so as you can see the figure, what is the difference between this value and this value? This, right? So EF. So I'm directly writing that as TF divided by original length of the diagonal. As you can see in the figure, A root 2. A root 2. A root 2 is sense of what is meant by A. A is nothing but length of AB. So you can write this as AB root 2 also. AB root 2. Okay. So length of the diagonal AB root 2. So EF divided by, instead of dB, diagonal length of the diagonal, A root 2, which is equals to EF divided by AB root 2. Okay. So now let us consider triangle BEF. BEF. So if you see, this is 45 degrees approximately, right? Isn't it? So this is going to be 45 degrees and this is 90 degrees. So EBF is a right angle triangle. So therefore you can apply the trigonometric formulas and all. Okay, I hope you know that the trigonometric formulas are applicable to this right angle triangle, sine, cos, tan and all this. So let us resolve this length over here, EB. Okay, it is substitute, this is the horizontal, let's take this as horizontal, and this is the length EB. Resolve this length EB into this direction and into this direction, into this. Okay, so as this EB is making an angle of 45 degrees with this side EF, this will be the cos component, this will be the sine component. So this will be the, what will be the value of EF? EB cos 45. I hope you understand, right? This is the right angle triangle. So let us resolve this EB based on this angle. As AB is making an angle of 45 degrees with this EF, this will be the cos component, this will be the sine component. So this will be equals to EB cos 45. So let's see here. So therefore, from triangle BEF, angle BEF is approximately equals to 45. Therefore, EF equals to EB cos 45 degrees. So let's replace the values over here. So EF can be written as this. So EB is written as EB cos 45 degrees divided by A root 2. But see in this figure, this is phi, which is very much smaller, and the tan of this phi, what will you get? Tan of this phi is equals to opposite side EB divided by adjacent side AB, isn't it? Right, see here. So tan phi is equals to EB by AB. Of course, EB by A, which is, as you know, AB is the side of that body, so which is equals to A. So send this A over here, you get EB is equals to A tan phi. So EB equals to A tan phi. So therefore, finally, straining diagonal BD is equals to, just simply put the values here. So in place of EB, put the value A tan phi. So A tan phi cos 45 A root 2. A cancels and cos 45 is 1 by root 2, 1 by root 2. So root 2 and root 2 get multiplied and becomes 2. Therefore, what remains is 1 by 2 tan of 5. So just write it down here. Tan 45 equals to 1 by root 2. Okay, so tan 5. So as you know, as phi is very much smaller, tan phi can be written as 5. So strain in diagonal BD is equals to half of 5. As you can see, the strain in the body is equals to half of the shear strain, isn't it? Right? So now we know phi is equals to shear strain since rigidity modulus C from the definition is equals to shear stress by shear strain. You can send this and bring this here. So shear strain is equal to shear stress divided by rigidity modulus. So place this term in this equation. So you get finally strain in diagonal BD is equals to half of tau by chi. Okay, sometimes in examination he may ask you to show, prove that the strain in the diagonal BD is equals to half of shear strain when a shear stress of tau is acting on a square body cube. Okay, this is how he's going to ask to derive the expression here. Right, so let us go into the next canvas. So due to this shear now, so now you understood that because of that shear force, shear stress acting on the rectangular body, there is a shear strain in the diagonal, right? I mean, there is a strain in diagonal, not a shear strain, just a strain. So the strain is equals to half of phi. Okay. So now because of the uh, shear stress which is acting on this body at the top of the rectangular body. Okay, as you know, BD is the diagonal and AC is the diagonal from the figure. If you see here, okay, BD is the diagonal and AC is the other diagonal. But because of the shear stress acting over here body, the body tends to bend in this direction, distort, deform in that direction. So now what happens practically, you can assume what is going to happen, right? So the diagonal DB is going to experience tensile stress because of this shear stress. So this shear stress is actually giving rise to a normal stress in BD. Okay, and at the same time, in the diagonal AC, because of this shear stress, there is going to be a compressive stress being developed. So as you see here, tensile stress of sigma BD is developed in BD diagonal, and the compressive stress of sigma AC is developed in AC. Okay, so in BD, tangential stress, and in AC, a compressive stress is going to be developed. It is to be noted that the magnitude, the value of tensile stress and compressive stress in the diagonals is actually equal to the externally applied shear stress tau. Okay, of course, sorry, yeah, just I changed the sign convention, so let it be tau. So the normal stress in the diagonals, tangential and compressive, is going to be equal to the shear stress in terms of magnitude. Okay, so now you can rewrite the equation for strain in diagonal in another way, in a second way, in a different approach. Okay, how can you write that? As we seen earlier, in case of volumetric strain, we have taken a solid body, three-dimensional body, and we derived the expression for net strain, isn't it, in x, y, z directions. So let us do the same thing. So here, as you can see, there is a rectangular body over here. This is diagonal 1, this is diagonal 2, this is A, B, C, D. There is a tensile force sigma T, which is equals to sigma, which is equals to tau. Okay, we are denoting it with tau. Okay, and at the same time, there is a compressive stress acting here, which is equals to sigma C, which is equal to sigma equals to tau. Okay, same in magnitude among them. So this is happening. So when this is applied with a tau, when it is getting distorted in this direction, okay, what is happening is this is going to experience tensile stress and this is going to experience compressive stresses. Okay, as you can see here, so see here the shape of this. Let me show you here itself. So as you can see, the length of the BD has been increased. That means a tensile stress is actually responsible for this thing, right? And at the same time, the distance between AC has been changed to AG, right? Diagonal length. It has been shortened. See here, this is the diagonal AC, but after deformation, the length of the diagonal has been decreased. So when will that decrease? When a compressive force, compressive stress is developed in that diagonal, isn't it? Now you need to know that these both the triangles are at 90 degrees, 90 degrees, isn't it? So if you see here, the strain in diagonal BD, the net strain in diagonal BD will be equals to the longitudinal. See here, longitudinal strain in BD due to the tensile force acting. Okay, but since there is a compressive force acting in the perpendicular direction in the AC, because of this compressive stress, there is going to be a lateral strain again in this direction, isn't it? Right? So you need to minus these two or add these two. That depends on what this lateral strain is. Okay, positive or negative. Let me deal with that. So as you can see here, because of the tensile stress acting in the diagonal BD, there is going to be a longitudinal strain in BD due to tensile stress sigma BD, which is equals to tau. Let me change this. Okay, tau. Okay, and at the same time, because of the tensile stress, compressive stress acting in the C and A, okay, C and A, there is going to be a longitudinal strain in AC, but at the same time, in the other perpendicular direction, longitudinal and lateral are perpendicular to each other. So if AC is taken as longitudinal direction, BD is the lateral direction, isn't it? So because of the stress tau, compressive stress tau in AC, there is going to be a lateral dimension, the lateral direction, lateral strain, right? Because of sigma C. So there are two strains in BD, right? Longitudinal strain because of tensile stress and lateral strain because of compressive stress in AC. So what should you do? Should you add both of these terms or subtract from one another from each? Okay. So what we are going to do is, so here see the second term, I just wrote it here, lateral strain in diagonal BD due to compressive stress in AC. Now I used a symbol minus over here. Why is that? Why is that? So because of this reason. Okay, because this strain, lateral strain, as you can see in the previous sign convention, a strain is taken to be positive. Okay, so positive if the length of that dimension has been increased, length or dimension has been increased because of this strain. Okay, so what is happening here is, because of the compressive force, because of this compressive stress, the lateral dimension which is present developed in BD is actually helping this BD to stretch, isn't it? So this and this get cancelled. What happens is you get a plus here. You need to add here. Okay, this and this get cancelled and this becomes minus into minus plus. So as we seen earlier, if a strain is responsible for the increase in length or dimension, it is positive. So here the lateral strain is responsible for the additional increase in length of that diagonal dB. Okay, so that is why we are using a plus symbol. Okay, in different cases you have to add minus also. Okay, in different cases, so, as we seen earlier. So you need to properly decide this. So now simplify this equation. Sigma BD by E is nothing but longitudinal strain, and of course, as I said, this cancels and becomes plus. Okay. So what is this? As you can see here, mu AC is equals to lateral strain in BD divided by longitudinal strain, right? Lateral by longitudinal. Okay. So this is what happens. Okay, this is longitudinal. This is lateral. It is shown I am denoting it this BD. BD represents the direction in which the lateral strain is going. In AC, if it is going a longitudinal strain, the lateral direction is BD, right? So I am representing that. So now epsilon BD can be written as mu into AC into epsilon AC as shown in this figure. So now, of course, we can write simply AC here. So sigma BD by E plus mu into sigma AC by E, because you can write straight from our basic formula. Stress E equals to stress by strain, strain equals to stress by Young's modulus, E and RH. Of course, you know sigma AC and this is the compressive stress in AC, that is equals to tau 1 మనం already చెప్పుకున్నాం, right? So I'm just replacing it with tau. Okay, so take tau by E as common, so 1 plus mu into tau by E. But we have two equations, right, for BD. This is the expression for BD, which is equals to 1 plus mu into tau by E, which you got from this equation. But previously we have derived another equation here. Strain in the body is equals to, diagonal BD equals to half into 5, half into tau by G. So now let's equate these terms over here. 1 plus mu tau by E equals to half into tau by G. So tau get cancelled. What remains over here is E is equals to 2G into 1 plus mu. This is equals to 2G into 1 plus 1 by n. You know that mu can be written as 1 by n, right? So this is equation. So this equation gives the relation between E and G. So today let us see the Generalized Foods Law. Okay. So in this, we consider a solid body in the form of a cuboid or a cube as shown in the figure. Okay. This helps us to understand the volumetric strain that is developed inside a body. Okay, so now let's get into this. So as you see, this is the body that is considered a cuboid, and as you know, the cuboid has 6 faces, and on each face there is a normal stress acting sigma x on in x direction, sigma y in y direction, sigma z and sigma z in z direction. So this is x, this is y, and this is z direction. Okay. So now all the nature of these 3 stressors, sigma x, sigma y, sigma z, is compressive in nature. Tensile in nature. Therefore, the body is going to deform. So how is it going to deform? It is going to increase in its length, increase in its breadth, increase in its height in each and every direction. So let us see in detail about this. Okay. So as we know, E is nothing but Young's modulus, which is defined as tensile or compressive stress divided by strain. Okay, and simply we write this as E equals to sigma by epsilon, and therefore just interchange them. Epsilon is equals to sigma by E. So therefore, epsilon of x, I mean strain in x direction is equals to, so what happens is stress in x direction divided by E. So that is what I wrote here. Okay, so this sigma x is nothing but the strain in x direction due to sigma x. In the same way, epsilon y is equals to strain in y direction due to sigma y, which is written as epsilon y is equals to sigma y by E, and epsilon z is equals to sigma z by E. So if you see here, sigma x is the normal stress acting on this face, isn't it? So this strain that is caused in the x direction because of this sigma x is nothing but longitudinal strain in x direction. So that is what we call, right? The strain in the direction of the load is called as longitudinal strain. And the strain that is taking place in the perpendicular direction is lateral strain. So we are going to see a little bit about that too. Okay, so now sigma x is nothing but the longitudinal strain in the x direction because of sigma x. Sigma y, sigma z are the longitudinal strains in y and z direction because of sigma y and sigma z, normal stresses. Okay, so here. Okay, so now we also know that Poisson's ratio, which is denoted by mu or 1 by m, is equals to lateral strain by longitudinal strain. Okay, so let us see that. So now let us consider all these expressions in order to give the equation for volumetric strain. Okay, so we are trying to give an equation for volumetric strain here. So in order to do that, we just need to have an idea about these equations. Okay, so let us go into this. So now there is a lateral strain in y and z direction due to stress in x direction, isn't it? Right. So as sigma x is acting in the x direction, there is a longitudinal strain of sigma x by E. And at the same time, along with this longitudinal strain in x direction, there is also a lateral strain in y and z directions. Okay, we have seen the lateral and longitudinal strains when we discussed in lecture 2 about strains. Okay, so this is the longitudinal strain because of sigma x, and this is the lateral strain in y and z direction because of sigma x. Okay, so now as you see here, we can write the expressions for lateral strain in y and z direction due to sigma x in x direction. Okay, so how do we write? So lateral strain in y direction due to sigma x is epsilon y is equals to mu into epsilon x. So how did I get that equation? It is simple. Okay, so for now just forget about sigma y and sigma z. Just only think about sigma x. Okay, see this figure. Forget about sigma y and sigma z. Just see sigma x. So because of this sigma x, the length is going to increase, isn't it? So there is a longitudinal strain which is equals to this value, but at the same time, perpendicular to this longitudinal strain, we have a lateral strain. So what are those directions? This is the longitudinal direction, strain direction. So the lateral strain will be in Z and Y, which are perpendicular to X and Y. Okay. Now see here, see this. Mu equals to sigma y by sigma x. As we know, lateral strain by longitudinal strain, generalized formula, right? Mu equals to lateral strain by longitudinal strain. So if in x direction, if you wanted to write this mu, you get two mu values, isn't it, right? Because there are two lateral directions to x. X కి పర్పెండిక్యులర్ గా ఉన్న డైరెక్షన్స్ ఏంటంటే రెండు, కాబట్టి రెండు లాటరల్ స్ట్రెయిన్స్ వస్తాయి అన్నమాట. సో కాబట్టి యూ కెన్ రైట్ టూ ఈక్వేషన్స్ ఫర్ మ్యూ హియర్. ఓకే, ఫర్ ఎగ్జాంపుల్ ఇఫ్ యూ టేక్ ఎ సర్క్యులర్ రాడ్, ఇట్ హ్యాస్ ఓన్లీ లెంత్ అండ్ క్రాస్ సెక్షనల్ ఏరియా, ఓన్లీ టూ. Okay, so delta L by L will be the longitudinal strain and delta D by D, change in diameter with respect to original diameter, will be the lateral strain. In that case, only one lateral strain. But in case of here, there are two planes perpendicular to x direction. Therefore, we have two new equations. So now, if I consider the lateral strain in y direction because of sigma x ఏమవుతుందంటే lateral strain in y direction because of sigma x at epsilon y divided by longitudinal strain in x direction, isn't it? అంతే కదండి, lateral y లో అవుతుంది, longitudinal x లో అవుతుంది. అండ్ అట్లానే ఇంకో మ్యూ కూడా ఈక్వేషన్ రాయొచ్చు, పాయిసన్స్ రేషియో, lateral by longitudinal అన్నాడు కాబట్టి. So I can write again with respect to z direction, epsilon z by epsilon x. So epsilon x is nothing but longitudinal as in the figure, as in the equation. And in the same way, lateral strain అంటే epsilon z. Okay, so now just simplify this. You can write epsilon y is equals to mu into epsilon x, and epsilon z is equals to mu into epsilon x, isn't it? So now just concentrate here. Lateral strain in y direction due to sigma x in x direction is epsilon y equals to mu into epsilon x. Lateral strain in z direction due to sigma x in y direction is epsilon z equals to mu into epsilon x. Similarly, just see the figure here. Now I hope you understand. Because of this sigma x, there is a longitudinal strain in x direction, and because of this sigma x, it is also responsible for two lateral strains in y and z direction. In the similar way, because of sigma y in y-axis, there is going to be a longitudinal strain in y direction here, and at the same time there is going to be a lateral strain in x and z direction. Okay, and similarly, because of sigma z in z direction, there is going to be a longitudinal strain in z direction and also a lateral strain in x and y directions because of sigma z. Okay, I hope you understood here. So similarly, you can write as we wrote for x, you can also write for y here. See here, similarly, there is lateral strain in x and z direction due to stress sigma y in y direction, isn't it, right? So again you can write this equation. Okay, consider the sigma x. Okay, if you consider sigma x, epsilon y is the longitudinal strain, isn't it? Okay, in x direction, epsilon x is the lateral dimension, lateral strain, and in case of z direction, epsilon z is the lateral strain. This epsilon x and epsilon z are nothing but the lateral strains because of sigma y. Okay, so now as we did earlier, just interchange this. So I can write epsilon x is equals to mu into epsilon y. In the same way, interchanging this, epsilon z is equals to mu into epsilon y. Therefore, if you see here, epsilon x and epsilon z are nothing but the lateral strains in x and y direction because of stress sigma y in y direction. Okay, so now if you see here, the third one, similarly, there is a lateral strain in x and y directions due to stress sigma z in z direction. Okay, isn't it right? So lateral strain in x direction due to sigma z. If you want to calculate this, just take and write the Poisson's ratio equation, right? So since sigma z is the stress, okay, epsilon z is the longitudinal strain in z direction. Therefore, epsilon x and epsilon y are the lateral strains in x and y directions. So interchange them. Epsilon x equals to mu into epsilon z, and interchange this, we get this. So if you observe these equations here, these two and these two, 1, 2, 3, 4, 5, and 6. If you see, observe these 6 equations and this figure here. So because of sigma x, there is one longitudinal strain and there are two lateral strains. Similarly, because of sigma y, there is one longitudinal strain in the direction of y and there is lateral strain in x and z direction. And because of sigma z, there is a longitudinal strain in z direction and the lateral strains in x and y directions. Therefore, in the direction of x, there is going to be a longitudinal strain and two lateral strains, isn't it? See, just see here. So this is the longitudinal strain because of sigma x in x direction, isn't it? But if you see here, this is nothing but lateral strain in y direction. And if you see here, we have lateral strain in x direction due to sigma. So in x direction, we have lateral strain due to sigma z, and in x direction, you have lateral strain because of sigma y, and in x direction, you have a longitudinal strain because of sigma x. Okay, similarly, if you see here, there is a longitudinal strain in y direction, and similarly in y direction there is a lateral strain because of sigma x, and also there is a lateral strain because of sigma z in y direction. Okay, so I hope you understood here. Okay, so now what I am trying to write is the net strain in each direction, because this is the longitudinal strain in x direction, but there are two lateral strains also in x direction. So I need to add a longitudinal strain and the lateral strains in x direction to get the total or net lateral strain, net strains. Okay. So similarly, in order to get the net strain in y direction, I need to add the longitudinal strain in y direction and also the lateral strains in y direction. So in order to get the net strain in z direction, I need to add longitudinal strain in z direction and the two lateral strains in z direction because of sigma x and sigma y. Isn't it right? Okay, so now let us try to write these equations here. See, as you see here, we need to follow this sign convention. Okay, we need to use plus sign for a strain due to increase in length if there is increase in length. Okay. The strain calculated is equals to increase in length to original length అయితే plus sign. Negative has to be used for the strain if strain is decrease in length to original length. Okay. If the strain is because of decrease in length, negative, plus if the strain is because of increase in length or dimension. Okay. So now let us go into this. Therefore, the net strain in body in x direction is, so carefully observe this equation. Okay. So what is going to be? The net strain in the body in x direction is x direction లో ఏముంటుందన్నమాట 1 longitudinal and 2 lateral ఉంటాయి. Longitudinal strain is because of sigma x, whereas lateral strain is because of sigma y, and other lateral strain is because of sigma z. Okay, so all these strains are in x direction only. So now I have used negative symbol for lateral strains and positive for this. So can you tell me why it is? So as you see in this figure, this is a tensile force acting on the body, isn't it? So as you see, the longitudinal strain is positive because as this is a tensile stress, the length is going to increase. The longitudinal direction, in the longitudinal direction, the length is going to increase, L, isn't it? Therefore, it is positive. But because of y, sigma y and sigma z, when it is pulled this way, okay, if you are trying to pull this way, what happens is the lateral strain in the x direction is negative because the length is going to decrease. The width and height is going to decrease. Okay, so you need to observe that. Okay, just like a rubber band, if you are trying to pull it, the length is going to increase, but the lateral dimension are going to decrease. So if it is a tensile force, remember that. You can just bluntly remember also, if it is a sigma x is tensile stress, the longitudinal strain will be positive, lateral strains will be negative all the time. If the sigma x is compressive in nature, longitudinal will be negative and lateral will be positive. Quite opposite. Okay, you remember one thing and you can also, you can easily write the other one. Okay, remember this. If sigma x is a tensile stress, the longitudinal strain is positive and lateral strains are negative. Therefore, since sigma x is tensile in nature, I used plus for that, and for lateral I have used negative symbol. Okay, so because of sigma x, the length of the cube or body is increasing, but because of sigma y and sigma z, due to the lateral strain, it is actually reducing the strain in that x direction. Okay, so now since E equals to stress by strain and the strain is equals to stress by E, okay, you can write these equations in this, and we can see here sigma epsilon x equals to sigma x by E, as you know, minus. I'm just using the previous formula. So okay, what is it? Lateral strain in x direction due to sigma y. Okay, next direction because of sigma y. Lateral strain in x direction due to sigma y. What is it? Sigma x, epsilon x equals to mu epsilon y. So this is the lateral strain in x direction due to sigma y. So mu into epsilon y. And in the same way, in the x direction due to sigma y is mu into epsilon z. So minus mu into epsilon z. Okay. So as you know, epsilon y can be written as sigma y by E, isn't it? Just like this. this. Okay, V equals to stress by strain. So strain equals to stress by E. Okay, so if I'm talking about epsilon y, what I should write? Stress in y direction divided by E. Right? And if it is epsilon z, stress in z direction divided by E. Okay, so now by substituting, I got this equation. So now this equation represents the net strain in the x directional matter. Okay, so this is the longitudinal strain in x direction because of sigma y, whereas this is the negative lateral strain in the x direction but because of y in z direction. Okay, similarly, you can follow the same equation, and can write for sigma y and sigma z also. Okay, but due to symmetry, I can easily write without deriving them, such as here epsilon x cube. This is how you wrote. So sigma epsilon y is equals to just like x y sigma y by e minus mu into sigma x by e minus mu into sigma z by e. So we are talking about y, so y remaining x and z. So similarly, epsilon z equals to sigma z by e minus mu into sigma x by e minus mu into sigma y by e. Okay. So if you wanted to just verify, you can do the same process which I have done here. Okay, and can obtain these equations in y and z directions. Therefore, this is the net strain in y direction, this is the net strain in z, and this is the net strain in x. See here, if there is no lateral strain in any direction because of sigma x, sigma y, sigma z, then this term and this term, this 2, 3, 4, 5, 6, all these 6 terms are going to be 0. Okay, at that stage, epsilon x will be only this value, sigma y, epsilon y equals to sigma y by e, epsilon z is equals to sigma z by e. Okay, when there is no lateral strain in a body. Okay, in such case, even this mu is going to become 0. Poisson's ratio will be equals to 0 if lateral strain is 0. So this is all about the volumetric strain. Okay, so this is the net strain in x direction, this is the net strain in y direction, this is the net strain in z direction. Therefore, the volumetric strain sigma v can be written as, epsilon v can be written as epsilon x plus epsilon y plus epsilon z. Okay, so I hope you understand this. Let us see the relation between E and K. E is Young's modulus, K is bulk modulus. E is equals to stress by strain, longitudinal stress by longitudinal strain, or lateral stress by lateral strain, whereas K is equals to normal stress by volumetric strain. Okay, we already saw these equations. So let me go directly into the derivation of these relations. Okay, so we have seen this equation previously in the Generalized Foods Law. Okay, what is this? Epsilon x is nothing but the net strain in x direction, okay, which is equals to longitudinal strain in x direction because of sigma x minus of lateral strain in x direction because of sigma y minus of lateral strain in y direction because of z. Okay, of course you can write in y direction and z directions also. Right? So here in order to derive the expression for these two, in order to establish a relation between E and K, I have taken a body as shown in this figure. So on each and every face, there is a normal stress of sigma, same value. So on the six sides, in x, y, z direction, there is a sigma, a normal stress acting on the body. Okay. So now I can just simplify this equation, isn't it? Right. So sigma is equals to sigma y equals to sigma z equals to sigma. Therefore, epsilon x is equals to sigma by E minus of mu into epsilon by sigma by E minus mu into sigma by E. So we have common and these two are the same terms. Therefore, by take this common and adding these two, we get sigma by E into 1 minus 2 mu. And similarly, we can write the similar expression for y also. And on simplification, you get epsilon y equals to sigma by E into 1 minus 2 mu. Similarly, in z direction also, epsilon z is equals to sigma by E into 1 minus 2 mu. Okay, so this is the net strain in x direction, net strain in y direction, net strain in z direction. So now, if you see this, volumetric strain is equals to summation of net strain in each and every direction in x, y, z. So epsilon x plus epsilon y plus epsilon z. So just substitute these terms and adding them, we get. So all the three are similar terms, right? So directly you can multiply with 3. Okay, so 3 into sigma by E into 1 minus 2 mu. Okay, so put it here like this, leave this here. Now see, we know that K, bulk modulus is nothing but normal stress sigma divided by volumetric strain epsilon V. So therefore, sigma by epsilon V, which is equals to sigma by, substitute the value of epsilon V in the denominator. This is what you get cancelled. Now K is equals to, sum this E at the top, E divided by 3 into 1 minus 2 mu. Okay, so now just send this also to this side. What do you find? Equals to, E is equals to, if you go this side, 3K into 1 minus 2 mu. Okay. So similarly, previously we have also established the relationship equals to 2G into 1 plus mu between E and G, X modulus and rigidity modulus. Okay. So now, using these two equations and equating them together, you can get an equation, okay, which establishes the relationship between E, 9, K and G. Okay, so here in this equation, we saw the relationship between E and K, here E and G, and here E, K and G.